Good morning to all. My name is Neethu Elizabeth Simon. I'm a software engineer working for Intel Corporation in Phoenix, Arizona. I'm really excited to be here and thank the organizers for giving me this wonderful opportunity to come and share my learnings with you all. I also want to thank yesterday's keynote speaker, Jennifer Prenke, since she provided the perfect introduction to what I'm going to talk today based on computer vision and data labeling. So you can consider her talk yesterday as a theory and the talk today as the application and, as students say, the lab, right? So there is this myth in the industry that you have to be an expert deep learning data scientist to build solutions, build smart solutions based on deep learning and computer vision. Through this talk, I want to bust this myth that you don't need vast programming expertise or complex tools to build these smart solutions. I want to take you all through this journey on how to implement a vision-based deep learning solution using simple open source tools. So when my friend's aunt and uncle migrated to US back in the 60s, the aunt was not very fluent in English. They once decided to go into a grocery store to shop. The aunt was going through this aisle and she saw this can of food and was really interested to see Grandma Z's super premium Simply Chicken. She picked it up looking at the label because it was very interesting. And then she thought, maybe I'll cook chicken soup for dinner today. She showed it to the uncle and he was astonished. And he asked her, do you want to feed dog food to your family? She picked up the label, she picked up the can of food looking at the label without realizing that it is dog food. Dog foods these days come in fancy cans. Now imagine yourself being in a foreign country and walking through their grocery aisle. You're going to see all these cans of foods with these different items, and you're going to get overwhelmed because you don't understand the language. You can't read what is written on the cans, right? So you start looking at the label. And then your brain will try to correlate the images that you see on the can with something that you would have seen before. And based on this assumption, based on this prediction, you pick up something which may or may not be exactly what you were looking for. Now, what if you had a computer system or a mobile app that you could just go scan the image, and then it's going to tell you exactly what the object is? So today, I'm here to take you all through this journey on how to implement such a solution using computer vision data with simple open source tools. I will also cover the challenges faced by the industry today in the large-scale development of such solutions. So before we move into the solution implementation, I want to take you all through my journey. I want to introduce myself and share my journey with everyone here. So I have to state this, that I'm not a data scientist. I worked as a Java developer back in India and decided to come to US to pursue my master's from Arizona State University. I started working for Intel as a C# developer, and currently I'm working as a software engineer in the solutions engineering group of Internet of Things group at Intel. So my background has been in developing software applications. However, all these innovations being made in IoT, AI, machine learning fields is slowly but steadily transforming me to work in this vast field. I started off learning how to collect data from sensors, how microcontrollers work, how do you integrate these sensors into microcontrollers. So one of my projects for testing, I had built an air quality monitoring system using Arduino and sensors to collect the amount of carbon dioxide and oxygen in the atmosphere. And currently, I'm working on how to analyze these data to build smart solutions for our customers, especially the computer vision data. So I'm not a data scientist, but a solutions engineer. And solution engineer sometimes is also nowadays being called as data engineer or a machine learning engineer, depending on what the domain is. This talk here is based on my learnings working in this field for the last couple of years. So before I go into that, I wanted to share that I'm also passionate about diversity and inclusion initiatives. I lead one of the employee resource groups at Intel, focusing on career development and providing volunteer opportunities to employ. I'm also passionate about STEM education for kids, and I had mentored a group of kids last year for the fall first Lego League robotics competition. Apart from that, I'm also a part of the professional club crew team for Dragon Boat paddling. Dragon Boat is a very famous sports in China, which is very popular here in US and Canada. And we are preparing for our World Championship next year in France. So coming back to our talk, IoT, or Internet of Things, as you all know, is a web of numerous devices connected together and communicating with each other with minimal human intervention. Massive number of devices are getting collected every second. They are communicating, collecting, and sharing data. Gartner actually predicts that 14.2 billion devices are going to get connected by end of this year. And this number is going to reach around 25 billion by 2021. So thanks to cheaper and faster processors and wireless networks, we are seeing innovations in IoT, which is bringing this digital and physical worlds together. Since these devices are getting connected and communicating and collecting and sharing data with each other, we can build smart systems. These smart systems can computationally analyze large sets of data and reveal patterns, trends, and association. So we use vision every day to make sense of the world, but our eyes are just a window. The visual cortex in our brain actually gets the data from the optic nerve, which provides us the understanding of our surroundings. So as the Internet of Things is coming to life, number of things getting installed is just growing. Camera can be considered as this ultimate thing sensor, which is generating enormous amount of visual data. In the present world, a picture is worth 1,000 words. But for a developer, this is a vast repository of data. The ability to derive sense from this massive flow of data from cameras is now becoming critical. So with advances in deep learning and computer vision, the ability to build a digital cortex for inferring objects in an image or a video feed is becoming faster and easier than ever before. So video, along with computer vision and AI, is now termed as the eye of IoT. So before we move into the solution implementation, let's take a look at the video in the next slide. So this is a perfect example on how not to build a system, a smart system, in the real world today.
Playing jazz.
Playing jazz.
Smoothie.
Making smoothie.
Calendar.
No meetings today. Remember, dentist at 9:30.
Fire off.
Fire off.
Open door.
Door open.
And we're gonna do one more.
Oh yeah. Open door.
Wrong voice command.
Open door.
Wrong voice command.
Open. Open door.
Repeat that.
Open door.
I didn't understand that.
Hey! Open door!
Play on the floor.
Get over the door! Open the door!
Wrong voice command. Error.
Hey there. With a rock? Open door. Open door.
So that was an advertisement from a lock and key company. So that's how you not build a smart solution. So now let's come back to our grocery use case, where you have to detect objects looking at the image or the video feed. So for using a system like this, you need to have a large set of data. And I wanted to cut down my data set. So I just decided to pick 2 items. So I'm from India, so I love my Indian spices. So just decided to go with a data set of Indian spices. The system is going to detect dried chili peppers and cinnamon sticks. So what are the steps involved in developing a solution like this? There are 4 main steps. First is data collection, data annotation, the training, and then inference. So the first step is data collection, where you acquire the data and then prepare it appropriately. I'm assuming most people here are data scientists or data analysts who know what web crawlers or scrapers are. Web crawling is these internet bots that can go through the web browser and collect or extract useful information from there. And scraping is the process of extracting useful information from a given web page. These are some of the open source packages which are already available. So if you're a Python expert, you can just write your own web crawlers and scrapers, but save time and use these packages to do that. Request package can be used for web crawling, and parcel and beautiful soups can be used for the scraping process. So for my grocery use case, I had written a Python script using request and beautiful soup. The other options available are these frameworks or tools called Scrappy, PySpider, Mechanical Soup. PySpider has a UI which can track multiple crawls. And Mechanical Soup is also based on this beautiful soup package. So if your crawling needs are very minimum, you can just go with Mechanical Soup. The other way I collected data is using video. So for images, I used the script to download images from Google. I went into a grocery store and got video of actual spices from there. And I also downloaded videos from the Google, which describe these different spices, giving me a rich set of data. So the next step in data collection is the pre-processing, which is the difficult task, right? Which is data cleanup. So you have to remove any bad or unrelated from your data set, or else your model is going to perform really bad. So as you can see here, I want to train with an actual cinnamon stick and not cinnamon rolls, which is going to mess up my system. So what I did is manually inspected the images that were downloaded and deleted all those unrelated data which I didn't require for the training purpose. The next step is data annotation. So this is where you label the data. This is where you establish the ground truth. After you collect the data, you divide it into your training set and the test set in usually a 70 to 30 proportion. So this is the most simplest step out of all the 4 processes, but it is a really cumbersome task, specifically if you're doing it manually. So the object that needs to be detected in the training image, you mark them in these bounding boxes as shown here. Now, these are some of the open source packages readily available for you to do data annotation. Every tool requires us to draw these rectangular bounding boxes around the object that needs to be detected. And what differentiates these different tools is the features that they provide. In some cases, instead of a rectangular box, you could just draw a polygon or a cubic. Other features are like, can you read a CSV or a JSON or an XML format? I've also listed some paid tools here, Labelbox, Data Loop, and RectLabel. Data Loop actually claims to have automated this whole process using AI. So lesser the manual work, faster would be to develop solutions. Now, video is nothing but a collection of frames. Frames can be considered as images. Imagine extracting single image from each of these videos and then trying to annotate your data. That's going to be a very cumbersome task. So this tool called Computer Vision Annotation Tool, or CVAT, it's an open source tool which has semi-automated this process of labeling. So what it does is you upload the video there and then go and draw these bounding boxes only on the key frames. For the other frames, the tool automatically interpolates and then does the labeling for you, thus saving time for you. The other advantage of using videos is you can build a really good set of data for you, because the objects can be in different orientations, different angles, different lighting conditions. So you have this whole rich set of data to play around with. So as you can see here, on the left side is the images I had labeled cinnamon sticks and dried chili peppers with their labels. And on the right side is the tool that I used. The tool is called Boop's Python package. I know the name sounds funny. Please don't get offended. But that is the name of the Python package. It is a very useful tool because I just had to upload the image and then mark these rectangular bounding boxes around it and download the labels directly as an XML format, thus saving time for me. So it overall took me around 2 to 3 hours to finish annotating about 1,000 images. The next step in solution implementation is training. So training is where you build the analytical model for your object detection. As you can see here in the figure, the images along with its labeled data is fed into this deep neural network, which generates the model weights as the output. A deep neural network consists of several layers, and most of these have a very heavy architecture. The models need to be constantly improved to meet the performance and accuracy objectives. So the main advantage of using a deep neural network is because it can learn complex things. However, it requires a lot of data to train it. So the output from this whole process is the model weights, which we use in the next step for inference. But before we move into that, there are a couple of things to be considered when you're going to train for your data. The first thing is data. What is the complexity of data that you have? What is the type of data? How much of a data you have? Now, visual data is more complex than data from sensors. Will your system be able to handle so much of data? What kind of database do you have to use to store all this data? All these are design considerations you need to make before you start training. Now, also there are several pre-labeled data sets readily available. All these Pascal VOC. Coco is from Microsoft. Kitty, ImageNet is generated using Amazon's Mechanical Turk, Sun, and so on. If you use these data sets, it's going to save you time in developing solutions. For example, consider an application that you're developing for autonomous vehicle. You already have the data set available here. You could just use all these and detect the different objects on the road, like vehicles and pedestrians and traffic signals. You don't have to go and do the whole annotation process again. So as I mentioned before, if you want to use custom data, it is time-consuming and very, very expensive process. The second thing to consider is the compute platform, which is completely dependent on the data complexity or how much of data you have. Also, we have to determine whether we want to do training on cloud or on the edge. So what is edge? Edge is a device which is very close to the data source. It's not connected to the cloud. There is no internet connectivity. It helps for faster and secure processing of your data. Consider an autonomous vehicle, right? You cannot have server constantly communicating to the cloud there because it is very expensive. Wireless networks are expensive. And imagine having 1,000 vehicles connecting using this wireless network and connecting to cloud. The company is going to go bankrupt. So you can decide, so for the autonomous vehicle, you could have a server just running on your car and then collecting all these sensor data, all these data coming from the camera there to generate the model using training. So you could use an Intel Xeon or a core processor or maybe a lower end processor like an Atom. So this decision, whether you want to do it on cloud or edge, is completely based on the platform complexity. How much compute is required during training? What are the power consumption requirements for your use case? It's completely dependent on that. So for our grocery use case, I had used the Intel Core processor along with the GPU. The next thing to consider is the object detection algorithm. These are some of the very popular algorithms available for you to play around with. YOLO, which is you only look once, SSD, single-shot multi-box algorithm, RCNN, fast RCNN, faster RCNN, RFCN. These are all available in open source. Now here is where the expertise of a data scientist comes into play, where they develop these different algorithms, and they're constantly working on improving these algorithms for performance. So the ability to reduce the size of your model, but keeping the performance the same is an active area of research. So imagine in the future, you may want to use the training model on your mobile device, and you have to maintain the same performance, right? So from an implementation perspective, there is no perfect algorithm. In 2017, Google researchers had published this paper describing the speed accuracy trade-offs of these modern object detection algorithms. For real-life applications, we make choices to balance the accuracy and speed. So in the grocery use case, I had used this model called YOLO, just because it's smaller in size, it's faster to use, and it's easy to understand and configure. The last thing to consider is the deep learning framework that you want to use for training. These are some of the very popular ones: Darknet, Darkflow, PyTorch, and Caffe. One point to note here is when you select a deep learning framework, make sure the object detection algorithm that you have selected works on it. Most often, we select an algorithm and then find out that it's not supported on the framework. Also, make sure configuring these models are easier through the different frameworks that you have. Do remember that every tool takes input in a different way. So once you select the framework, figure out how is the input processing done. Do you have to do any pre-processing before you feed it into the framework? Also, are there any model optimizers available with the framework which can improve the performance of your model? So I had selected Darkflow to do training. Now, Darknet is written in C and CUDA, and it's an open source deep learning neural network, which is pretty fast. Now, Darkflow is a TensorFlow implementation of Darknet. And the reason I chose Darkflow is because it's written in Python, and TensorFlow, which is pretty easy to understand. Also, it's very easy, it's well documented, and it's very easy to configure the models there. So for around 1,000 images, it took me 10 hours to train. The model weight was around 800 MB. I stopped training once I reached an average loss of less than 0.9. So the minimum the average loss, better your performance of the model is. So as you can see here, I had used the Darkflow deep neural network. I fed all these image data along with the label data to generate the model weights. And all of this was just done using this single line of command here. So data scientists have really worked on these deep neural networks to make it really easier for people like me to use these things. So what we provide here is the set of data, the set of labels that we have generated, and the configuration file of these algorithms. This is what determines what the architecture of your deep neural network has to be. And you have to make sure that the number of objects that you are defining is set in this configuration files. Also the weights, the YOLO V2 weights here are pre-trained model weights. So you can just go to the website, download the weights, and then just reuse it for your training. Now the next step in the solution implementation is inference. So inference is where you use this trained model to make predictions based on the new data that you receive. One major requirement here is to be able to obtain faster inference rate. Now this is object detection in real time. So you cannot have any performance issues with respect to response time. Inference can again occur at the edge device, which can be a laptop, Intel NUC device, or a mobile device. Since it's happening very close to the data source, inference is going to be really fast and secure. So as you can see in the image here, I had the Darkflow framework, I passed the test images. I provided the model weights generated from the previous step, and then it predicted what the image is or where the image is. Again, all of this was just done with this single line of code. Instead of the test images, you can also provide videos to basically detect objects in them. Also, you can use the webcam on your camera. So in live scenario, it can record what is going on and then provide a bounding box around the object in that image. So I'll show you an example for that. So this is the result generated. As you can see in the first image, it is able to detect this one log of cinnamon, and it's failing to detect the other two. The confidence is pretty good at 87%. But in the second image, it is clearly detecting where the object is, but the confidence is very low at 0.06. In this slide, you can see the dried red chili peppers. The first image detects it's with a confidence of 95%, but the second one has a very low confidence of 0.02. And one reason for this is because most of the data in my data set were all dried chilies. The chili on the right side is a little ripe, so maybe it's not able to detect that. The other interesting thing to note here is it is detecting these human fingers as cinnamon sticks. That's because I didn't probably have enough, data to train this with. So as you can see, the system is not perfect. It is giving both good and bad data. So there are challenges involved in implementing these solutions. So object detection concepts have been around from the 60s. But faster and cheaper processors have made it possible to implement it in the last decade. The first efficient face detector algorithm that actually worked with a webcam was developed in 2001 by Paul Viola and Michael Jones. Soon, it got implemented in OpenCV, and face detection became synonymous with Viola and Jones' algorithm. Several new techniques based on computer vision and deep learning have since been developed in this field. However, industry still has not caught up with all these development in the field. We do not see large-scale adoption of these technologies in the industry today. So what are the reasons? So let's look at some of the challenges involved in implementing and commercializing a vision-based deep learning solution. The first is with respect to data collection. More the data you have, better it is. Your model is as good as how much of data that you have, how much of good data that you have trained it with. So as you can see here, it's detecting only the first block of cinnamon sticks and not the other two. And one reason for this is because I didn't have enough images of cinnamon sticks in this particular orientation or angle. So object orientation, angle, lighting, all these are things to be considered when you're training your data on images. The next thing is about removing bad and unrelated data. What determines a bad data? So for a simple grocery use case, it was very easy to know what is bad and what is good. Now imagine a use case on predictive maintenance of machines. You need to detect when the fault happens before the machine breaks down. So for example, there is an electrical surge, and you're collecting all these data from different sensors on the machine. So definitely for an electrical surge, you know that you don't need air pressure data to find the fault. But then what if the fault is more complex? You do need a subject matter expert to give you the knowledge for that, to define what is bad data and remove these unrelated data. So data scientists and solution engineers would need assistance from them. The next step, which is annotation, has its own problem of this manual versus automation. Manual annotation, as I mentioned before, is time-consuming, it is very expensive, and it is difficult to scale. So when your data is large, the cost to annotate custom data increases significantly. I earlier mentioned a tool called Data Loop. which claims to have automated the whole process using AI, but then it still needs some human intervention. It needs a manual inspection to validate the labels that are generated by it. So every annotation tool requires some amount of manual intervention to establish, validate, and fix labels. However, Amazon has actually crowdsourced this entire process of annotation. They provide this tool called Mechanical Turk, where you can outsource this labeling process to a distributed workforce who can perform this task virtually for you. Even Google uses crowdsourcing to label data. Have you noticed those CAPTCHA questions where it asks the user to detect which of the images have a particular objects in them? The most recent one is Facebook's 10-year challenge, where people were asked to post their current pictures with the ones 10 years back, which people claim that is being used to improve their face detection algorithms, because the user is just providing labeled data to them. So manual data annotation process is time-consuming, expensive, and very, very difficult to scale. So automation is the need of the hour. The next step is training, which is an iterative process. So deep learning algorithms are trained to learn iteratively on using data. A deep learned model is only as good as the data that you have. And the more powerful models you need to have varied data parameters and tuning to be done on top of that. So overfitting and hyperparameter optimizations probably are some known features that you all might know, but I'm going to try to explain it in a very simple way for those who are not data scientists. So overfitting is when your model has learned too much about your data. So it picks up all these noises and fluctuations in the data set as concepts, and then builds the model. And then when you get a new data, it's trying to apply all these concepts, which reduces the performance of your model. Now, hyperparameters are configurations which govern the training process. For example, the learning rate, the rate at which the algorithm needs to move across the image to detect objects accurately in your image. So when the data set is low, you go for a slower learning rate, or the epoch or the batch of images that you want to train together. And optimization or hyperparameter optimization is the process to obtain that optimal hyperparameters for your model. The process to get these hyperparameters and do data overfitting can be overwhelming if you're not a data scientist. So take the help from a data scientist or try to build up your skills on that. The last thing to note here is the compute. After data, the most important thing for training is compute. So if your training data is large, the compute required is large. And if you need to get a high compute device, it's going to be expensive to buy one. The last step, which is inference, is where you have to constantly update the models. Now, deep learning models perform really well in development environments, but they fail miserably in production environment. So models have to be constantly updated in order to maintain the accuracy and increase their accuracy level. There needs to be some feedback mechanism implemented to understand this new data, feed it into your training system, and get a new model. Most of the software companies or the web-based software companies have figured this out, do this really well, like Amazon or Facebook trying to do their digital marketing for you. But then companies that are working with sensors or devices are still figuring out this in the industry today. So complexity also increases with regard to designing the hardware, which again is dependent on the data that you have. So how many CPU do you want to have? How many GPUs? How many accelerators do you want to have in your platform? Last but not the least, the data privacy and security are of utmost concerns for the industry today. To sustain any successful deep learning solution based on computer vision, there should be some appropriate mechanisms used to secure data and avoid any kind of data breaches. So we are living in extraordinary times with continuous innovation occurring across technologies like AI, machine learning, computer vision, and the IoT. Fast and low-cost compute is enabling the development of these solutions across these technologies, leading to the widespread usage in different fields, like especially in autonomous vehicle, healthcare, industrial domain, and so on. So we have the knowledge and the tools readily available to work with massive amount of data that is generated every second. So through this session, we have busted the myth that you don't need vast programming expertise or complex tools to build solutions like these. With more innovations, implementing these smart solutions is going to get even easier and faster than ever before. Anyone can just do it. So with great data comes great power. With this great power of data and tools, let us build meaningful solutions to solve world's problems. Thank you. And yes, DC Comics and Marvel Comics can come together. At least the women can come together.